Yeah, good morning, good afternoon, good evening, everybody, and I welcome you to EMinar Day, Wednesday. And today we have a rather poignant talk from Graham Hill, talking about Phil Wannamaker. But before I do more introduction on that, just a reminder to those of you who came through a direct link that you can see on the MTNet EMinar page. You can see all the upcoming EMinars and register for them, and see the links to YouTube, the recordings and the presentations. And so for the rest of the month, we have three more exciting talks. One by Robert Grimm, who's going to talk on MT on the Moon next week, and then Alexander Graver on the electrical structure of the mantle using ionospheric, magnetospheric, and oceanic signals, which was his EMiW review in Turkey. And then the last of the month is from Nisha Schnepp on Tonga eruption, the EM induction. But today we have Graham, who will talk to us on From Salt Lake City to the Roof at the Bottom of the World, the works of Phil Wannamaker. And as I said, this is, yeah, it's a homage to Phil's contributions. Graham's a senior research scientist of the EM group in the Czech Academy of Sciences. I won't read out the CV, you'll all have seen it. And he did some pioneering work using MT for magmatic studies, and then worked with Phil very closely in the Antarctic. And he's an awardee of the New Zealand Geophysics Prize, the Antarctic Science Medal, and is a Lumina Quaruntu Fellow. So I'll stop the share, Graham, and invite you to come on in.
All righty. All right, has this worked?
Yeah, that's fine. Perfect.
Okay, good. Yeah, so thanks for inviting me to do this, Alan. And as you say, it's a privilege, but one I would rather not have. And yeah, I did a lot of work with Phil in the Antarctic. He's sort of the one who, not sort of, he is the one who introduced me to working there and brought me there. So I will probably I will focus mostly on the Antarctic stuff with a little bit of the work he's done elsewhere, which others are probably more familiar with, but just a little over. Okay, why is it? Oh, there. Okay, it's going. So, little overview of history about Phil, maybe to start with, right? He is Canadian. Grew up just in Ontario, a little ways outside of Toronto. Did his undergraduate schooling in geologic engineering at Queen's University in Kingston, and then moved to Salt Lake and never left, and had a pretty remarkable career as a soft money research professor for 40 years, which I think none of us would want to try to emulate at this point in the way science funding works. But he somehow managed to make it work. And he, you know, as others have said, he really enjoyed being out in the field and was often in the supervisory role, as you can see with these two photos, watching other people dig. So the top right photo is me trying to dig up an instrument that's been buried during a storm. And the bottom photo is actually the program director from NSF, who Phil has putting in a vertical. So not gonna really talk much about the intro to MT. Most people will have pretty good knowledge of this already. But in the Antarctic, the big thing is that you have some different considerations, additional considerations about potential non-plane wave effects. high contact resistance of the snow and ice, which Phil really was the pioneer of tackling these constraints. But before we get to Antarctica, just a quick review of sort of some of Phil's other work areas and studies. He I would say, so, and others probably can correct me, but he sort of had three big areas where he spent a lot of his career. One was on his career profile, and this is not all of it. I believe it had gotten into Kansas by the last I'd heard from him. So this is only showing it through California, Nevada, and Utah. But he'd also gotten through Colorado and into Kansas. And this really all stemmed from initial investigations he did looking at the Dixie Valley geothermal system and wanting to put the constraints on the multi-scale constraints on reservoir controls, and the large scale tectonic controls on these magmatic geothermal systems, which was where it started with Dixie Valley. And then he extended through the Great Basin and to the coast of California, and also eastward into Kansas eventually. And in this, he started with this work at Dixie Valley, where he had this small, tight, constrained model where he, had the magmatic input of the system, which he had constraints from drilling, and it all lined up. But when he took a bigger step out, he was able to see more controls of the underplating, of that there really wasn't a local source, local magmatic upper crustal chamber reservoir. So it was coming from a long distance with the large structural controls, and again, stepping out larger and larger. He really demonstrated the need for aperture in these investigations, and that these postage stamp size surveys don't give us the full picture. And he really was on the sort of forefront of what the key important structures are, right? Well before a lot of the rest of us, given his great geologic knowledge and skill set, in addition to his computational and numerical one. So Phil really was able to bring together large data sets in a way others couldn't, and saw the importance of these structural controls and weak zones before a lot of the rest of us, which has now become a really hot topic in magmatic studies. Paul Bedrosian's not so recent anymore. Mount St. Helens paper from 2018 was really focused on the role that these sort of crustal features and structures play in these magmatic systems, and Bill was onto that well before the rest of us. So, he was able to show that by taking these big apertures, you could really understand these systems on a larger scale, showing the difference between the Great Basin and the increased thermal activity beneath that part of the career transect that we could call it, and the sort of colder eastern Colorado Plateau. And sort of a second area that was of great interest to Phil was New Zealand, which this is a slide that he'd made that I had. where he'd done several high impact studies as well, looking at the Marlborough fault system, which hopefully you can see my mouse up here in the north, which is actually where I first met Phil, was as a PhD student with Hugh Bibby and Grant Caldwell. I got invited to come on the field work of that, and that's where I first met Phil. And Marlborough fault system is kind of right on the edge of the Hikurangi subduction, where it's sort of switching from a subduction from the west, and then further south we have the Fordland or Pusiger subduction, where it's coming from the west in the Fordland Pusiger, and coming from the east in the Hikurangi in the north. And he'd also done a large transect through sort of the central part of the New Zealand South Island as well, in the more compressional area, and had two results that showed, pretty dramatically different structures, with the northern Marlborough stuff, the top resistivity section, with the different fault systems all having their own sort of conductivity anomaly, and the fault systems sort of yanging westwardly. So the oldest, most developed fault system is, or yanging to the east, sorry, with the larger thrust system to the west. And he had his ideas on how that formed, and that these major fault systems were developed in large part due to fluid release from the subducting plates. And as they develop, they evolve from young strike slip near surface crustal features to larger big thrust systems as they become more as crust forms and develops, and the fluid from the fault system lubricates these brittle regimes. While in the Southern Alps, further south in the central part of the South Island, where it's the more compressional zone, he got this sort of banana-like model where you don't have the same fault systems coming to the surface, and he attributed that to fluids migrating to resistive stressed rocks that had been broken and were brittle, and then that these fluids could further induce failures. And he, like we all believe now, and that the earthquakes, they cluster around the edges of these fluid systems and are representative of the margin. The earthquakes occur on the margins of the conductors, and represent fluid movement. So that, I think, is sort of the quick overview of some of the non-anarchic stuff that Phil was interested in, and had great interest in, and was actually not finished with these areas. He was still working on his career profile, extending it eastwards, which Kevin Mendoza is doing some analysis of. Phil's last PhD student, and he had ideas about wanting to investigate the Fordland and Pusiger subduction system and the sort of transition from compressional regime to the subduction, and he saw this was an ideal place because of it being basically the birth of a new subduction system. So you could really investigate the trigger mechanisms for this and the tectonic initiation points, which was one of Phil's great strengths, was his geologic ability. But Phil certainly was the pioneer for MT in the Antarctic, and most of the MT work done in Antarctica, has his fingers in it somehow. Whether he was there or whether people were using technology that he developed, he really was the ice-breaking pioneer, so to speak. So with the Antarctic stuff, the first measurements were actually conducted at Vostok Station, which is here, and that was a telluric only measurement, and really only worked at the very long periods due to the high contact resistance. But that suggested that MT measurements were possible in Antarctica, and led to further work, and I believe the first measurements at Vostok were in the late 60s, mid to late 60s, and then the first sort of full MT measurements happened in the late 70s, early 80s, and they were here at the Pine Island Glacier. And that was it for a while, and that was the first sort of quantitative MT measurements were presented, and then nothing happened for a while until mid-90s or so, when Phil went to Central West Antarctica here and did the first sort of survey that wasn't just a couple point measurements and proof of concept. So in Central West, Phil did a 10 site profile, about 60 kilometers. And he followed that up at South Pole with another 10 kilometer or 10 site, 6 kilometer spacing survey. And then that was followed by work by Kate Selway and Jared Peacock at Davis Station, some work at Schumacher Oasis, and Discovery Island. But the Schumacher Oasis and Discovery Island were all done in exposed earth rather than snow and ice, so sort of a more standard MT measurement. And then Phil went and sort of changed the scope and scale of MT work in Antarctica, and did the work at CTAM, where he did a 550 kilometer long transect across the mountain range, which we followed up with a 3D survey of the Erebus volcanic system. And he recently actually reevaluated and got back into looking at his original surveys. So he'd recently computed an inversion for the first time of the Central West data, which when he initially did it was only forward modeled. And he'd re-inverted the South Pole data using the 3D code HexMT, which he developed with Michael Cordy. And the sort of updated, I wouldn't call it a new interpretation, but updated assessment of the Central West is is he basically got it right with his forward model, is what he said, which should surprise none of us. And that there was a very slight resistivity decrease at large depths that is required by the data it was required by the data and is indicative of a average mantle adiabat with temperatures of around 1600 Kelvin at 100 kilometers depth. Which is a little bit elevated to sort of a more standard dry olivine mantle mineralogy, which would have a temperature of about 1400 degrees Celsius at those sort of depths. And that the thickness of the lithosphere is, in agreement based on his MT work with, more recent seismic tomography with a, lithospheric thickness of about 100 kilometers, and that the sort of late Cenozoic volcanism of the region is not a widespread feature, and it's restricted to, again, coming back to this sort of structural control zone thing, restricted to crustal weak zones where it can take advantage of rift-induced weak spots in the crust and reactivation zones after the initial rifting period in the Cretaceous to allow the volcanism to happen. And of course, with the, like we talked about earlier, the postage stamp survey, he was advocating for, bigger aperture and extending data coverage to really be able to discuss and get a more refined image of the Central West zone. Whereas at South Pole, he again, done the same sort of assessment. And what is here? It's the same model using different starting models. So the first starting model used a half space underneath the thick ice coverage of a couple of kilometers, and the lower model used an averaged 1D profile as the starting model. So that's what the different starting models show, and they produce slightly different results, but the main sort of crustal and lithospheric, or at least upper lithospheric structure is very similar. And this work, showed also that once you got through the thick ice coverage of South Pole, which was not trivial, that there's these conductive zones which line up actually quite well with recent. So I think the South Pole work was completed in the late 90s and published in the early 2000s. And more recently, there's been some seismic tomography in the area which show localized low velocity zones in the upper mantle beneath South Pole, which align pretty well with the conductive regions that Phil's imaged. And the seismic models of Sam Hansen and Wissam Shan both suggest that there's an S wave velocity low that extends to almost to South Pole and has been interpreted as a modern lithospheric delamination event resulting from upwelling of the senosphere to near Moho levels and potential production of melt and underplating, which was sort of what Phil's model showed and his interpretation at the time. So, you know, he seemed to be, you know, the first one to have an indication of a magmatic thermal event taking place under South Pole region. But again, you know, he was advocating for bigger aperture, more data collection, and it was actually one of the proposals that we had submitted not too long ago, was to do another one of these long CTAM type transects that would have been further south, if you will, on the Transantarctic Mountains that would basically run into South Pole. So that's the quick summary of the first sort of ice-breaking Antarctic studies that Phil had completed. And now we'll just talk a little bit about some of the challenges that Phil basically provided the roadmap for how to overcome when working in the Antarctic or the Arctic, you know, in the polar regions. Let's be more general. This it applies to both the top and the bottom. So, you know, we rely on the plane wave assumption of our source field, and that produces what we call the convection electrojet, which on the left here is a sort of stable movement of from the dark side from the night side of the auroral oval to the day side, the plasma energy, and during the solar minimums, which is actually probably the better time to work in the polar regions, this is pretty stable. But in the more active part of the solar cycle, you can get these substorm electrojets, and those occur when the ionospheric tail sort of collapses back into the Earth, and it disrupts the sort of steady state convection of plasma from the night side to the day side of the auroral oval. And when that happens, you can end up outside of a plane wave source field. There's been sort of two approaches that have been taken for how to deal with this. One being removal of the non-plane wave, modeling out the non-plane wave source effects, or identifying periods when we have a plane wave source field. That was the approach that was championed by Phil, was identifying portions of your recording where you had, you know, a plane wave input signal. And this was done by looking at spectral amplitudes of the energy and dividing the recording. And what you observe when you do that is a sort of a daily 12-hour high energy period and a lower energy period. And what we did with that was we windowed the measurement and computed a response using only the high period energy, so the 12-hour segments of higher energy, and then the 12-hour segments of lower energy, compared them, and also a response with the whole sounding without windowing it, and effectively got the same response from all of these. This and a low activity level were indicators that the plane wave source was active. Others like Jared and Kate had done predictive modeling where they were using electric field and magnetic field relationships to determine that they were following each other as predicted in a plane wave setting. But largely the approach by the MT community has been to try to identify periods without that follow the plane wave requirement. The other big challenge for the measurement is the need to deal with the high contact resistance of the snow and ice. So the contact resistances in the snow and ice can be several mega ohms, which can easily lead to a pretty strong distortion of the MT response, especially at the high frequencies. So in order to deal with this, Bill, with John Stott, designed buffer amplifiers to basically transform the high impedance signal at the electrode and present to the data logger a more conventional output that resembles, contact resistance and signal that it's expecting from, a standard MT measurement in the dirt. And this, worked to great success. It enabled all of Phil's different campaigns down there. I believe that Kate Selway and Jared used a variation, if not these amplifiers, something very similar with their work at Davis Station, Prince Bay, and Kate's ongoing work in Greenland and possibly, I think, back in Antarctica. So with this approach and the inert titanium electrode sheets, which are very, very low, they are a pure titanium, not an alloy, so they're electrochemically stable, so they don't interact and create any surface charge. Has really made the MT measurement in the snow and ice possible, and so that it's effectively the same procedure with the buffer amplifier plugged in as a standard MT measurement. The other challenge of Antarctica is snow is a charged particle, so as it moves around, it's creating its own electric fields, and it's chaotic, and there's really nothing that can be done about it. Phil has done a lot of tests with trying to understand how this happens, or what, not how it happens. How it happens is, as the snow particles move, they heat up and you get charge separation of the positive H ions and the OH minus ions, with the H positive ions being smaller and more mobile and preferentially accumulating in the cold regions. So at the center of the snowflake. So as snowflakes move, they get frictional heating around their edges, and you get an OH negative build-up concentration around the edges. And then as they move, they also break. So you get these OH negative edges breaking off, and you get this redistribution of charge, creating these chaotic, localized, effective distortion sources that you just really can't do anything about. And they become a problem at about a wind speed of 8 to 10 meters per second, which is when you start to move into the saltation zone of saltation to suspension zone of particle transport, where things are moving not just along the ground, but up into the air and being airborne. And this had an effect pretty much over the entire range of the MT measurement. Phil did a lot of testing when he did the South Pole work, and saw this distortion was affecting at least to about 300 seconds on his responses. So the only solution that we came up with was, if you were working in an area prone to wind, was to put your measurement out for a long enough period that you caught a quiet period without wind. And then, of course, terrain is the other big one there, with crevasses and steep fields and dangerous places to work. So what we would try and do is, as you can see in the bottom right, we find a compressional zone, and we would attempt to stay at least a full dipole length from the expected hazard zone. Other challenges, are steep terrains as well, and we would handle this by moving around on skis and crampons and having rope practice to be able to excavate yourself from a crevasse if one happened to go into one. Let's see if this will work. This is just us clearing a site to make sure it's a safe spot to work. So I've got about a 2 meter long probe. There's Phil moving everything to the site center. If the snow is 2 meters thick without a gap, it's unlikely to collapse, even if it is just a large bridge over a crevasse. So that allows us to decide an area is safe to continue working. And yeah, steep snow-covered terrain, having to work with crampons and ice axes, move slowly, all these kind of things. Just get an idea of how steep some of the area was and how small the footprint where you can work on. So yeah, quite an interesting and spectacular place, but also quite challenging. And the weather can be another thing to consider. You don't want to get stuck in one of these storms, because it can last for a couple of weeks. And if you're out there, it's a pretty miserable place to be for 2 weeks. But this is that picture from the title slide where I was digging. So we put it in and it was a spectacular, calm day. By the time we finished putting it in, it had gotten quite ugly. By the time we came back, there'd been about 2+ meters of snow accumulation, and we actually needed to get a GPR to find the instrument. And yeah, this is, with the big winds that can come up, you can get issues with the helicopter and things like that, but no need to worry about that right now. This is a helicopter that had a rollover when it was trying to take off at the top of Mount Erebus, and has been up there for about 30 years now. Everybody was fine, but just the extra caution that needs to be taken in these environments. And everything takes way longer there. So in a 3-month season, this is just showing, when we worked and when we didn't. And in a 3-month season, we did about 50 measurements. So it takes a special kind of patience, which is something I think we all agree Phil was famous for. He could think about things for a long time and was able to deal with that sort of mindset of having to take your time and that things were out of your control quite often. So that's just an example of that. And this is 2 sets of equipment. So you have just so much more stuff when you're there than compared to a normal MT measurement, with the additional bulk of the buffer amplifiers and the titanium electrodes and the solar panels and everything else. It's just a lot more equipment to move around, plus your safety equipment and everything else. So this was at the CTAM camp in the Trans-Antarctic Mountains. And once you get it up and running, it looks much like any other MT site. And of course, we have Phil doing his famous topless MT that he had to do at least once on every campaign, even in Antarctica. But yeah, it's basically just a standard MT site. We have Yasu Ogawa, doing final setup and starting of the recording while Bill is burying the vertical, and we're about to head off to the next site. And this is just a time lapse of us putting in one of these sites from start to end. As you can see, it really is just the very similar to what you would do on a regular land-based MT site. Once you have the area clear and safe from any crevasse danger. So why go to Antarctica is a better question, right? I mean, it's far away, it's cold, got all these extra challenges. But actually, once you get there, it has great accessibility. You got huge logistical support from the different international programs. My experience is mostly with the US program and the New Zealand program. Others can attest to the support from the Spanish programs and the Australian programs. But you have this great logistical support. You have real the access is spectacular. You're not limited by where you can get typically, because you don't have forests in the way. You don't have to try and find a clearing. You don't have the local noise sources. And Antarctica is fabulously active geologic setting. So it's, it's got a huge rift running across it, separating East and West Antarctica. It's got active volcanism. So the later studies that I participated in with Phil, the big goals were looking at the rifting and extension. What is the mode of the mountain building? Transitions between the different support mechanisms and where they're located within the mountain range, the mechanism of the volcanism. The Transantarctic Mountains are probably the most striking and best example of a high rift shoulder in the world. It is the highest rift shoulder. So that led to the big questions of what's holding up this rift shoulder, and that was really, and so yeah, what's holding up the rift shoulder, and what is the control on the elevation decay as you move away from the rift boundary. That was the big focus of the long transect through the Transantarctics, and then the later work at Mount Erebus was, what is the main differences between a CO2 dominated rift volcano versus the more typical, well studied, H2O subduction related systems. And this is, where we went and had great success with the MT work, in large part because we were able to get, signals where seismology has had, some struggles. Just very difficult for active experiments to get energy to penetrate the insulating snow and ice layers, and they just don't have the sort of seismic coverage and instrumentation of other parts of the world. Obviously, it is very understandable to get the sort of tomography density needed for the same sort of resolutions we're able to produce with the MT work. So for the Transantarctics, which are, the boundary really between East and West Antarctica, the rift shoulder of the West Antarctic Rift System. There's the 550 kilometer long transect. Oh, I got these out of order, sorry. Way out of order. Anyway, so I'll try and adapt to that. This is the CTAM camp, which, as you can see, is a pretty big chunk of logistical support that was put in for a single summer field season. So the camp held about 100 people. The long tent here is the mess and living area. This is the sleeping quadrant. Some science office tents, some mechanics tents, latrine tent for washing and whatnot, a medical tent, storage area. And this camp had based at it two 212 helicopters, Bell 212 large helicopters, and a Twin Otter at all times, and was supported by LC-130 Hercules flights from McMurdo with supplies and personnel changes and whatnot, a couple times a week at least. So a big operation, which sort of indicates the amount of support you have in these situations. So this is the 3 mechanisms of potential support that have been discussed or proposed for the Transantarctic Mountains. You know, a thick mechanical crustal root. That's the first one. The middle one is a thermal upwelling, buoyancy, uplift process for the rift shoulder. Similar to what has, you know, similar to the support mechanism of the Great Basin in the US, where Phil's done a tremendous amount of work. And the third one being a non-thermal, long wavelength flexural uplift, cantilevered uplift. So each one of those would have a very different signature in the resistivity structure of the model response. So these are 3 different potential explanations that each will have a very different resistivity character. And here's some of the seismic tomography of the area, right? You see this is sort of the big divide between the active, warm West Antarctic zone and the cold Crotonic East Antarctica. And the CTAM profile is running kind of through here, just this side of South Pole, to about 85 degrees south latitude. And yeah, so the big question is, you know, what's going on with the rift? What's supporting the mountains? How are they separated? So to do this, you know, a 550 kilometer long profile with an additional bit of 3D coverage, just at this sort of transition between the sort of active stretching zone and the brittle, stable, non-deforming zone was completed over 2 field seasons. First field season was run out of that large camp that you saw earlier here, with primarily helicopter support for almost all of these orange dots. A few of the sites on the plateau were done by Twin Otter. The second season was a small camp of just Team Wannamaker. At these yellow sites were done by Snowmobile and Twin Otter support, and also up on the plateau by Twin Otter support. And this is sort of the large-scale geologic map of the area, where you can see the MT transect is located. And in a stable environment, you would expect to see sort of linear conductors along the terrain boundaries, sort of, you know, suture zones, if you will. And with these conductors being attributed to graphites or remobilized fluids and shearing. So with that idea, we did this profile, and you know, Phil was anything, he was able to interpret a sounding curve better than most. And you know, there's a very definite change as you go from the Ross Ice Shelf. So that's the bottom left of the map, through the mountain range onto the polar plateau. A very different structure to the sounding curves. And when modeled with with his in-house 3D code developed with Michael Cordy, he gets this result, which, you know, you don't have a big thermal upwelling underneath them. Oops, sorry, wrong way. Big thermal upwelling underneath the mountain range. So that sort of eliminates potential for, you know, thermal buoyancy being the cause of the high elevation, the high rift shoulder. We also don't see a really dramatic, strong, deep crustal root underneath the mountain either. So that, you know, by process of elimination, that sort of leaves the cantilevered flexure model, which is what Phil proposed and was maybe could be seen as being at odds with sort of similarly timed publication of a big scale seismic tomography model by Weiss and Shannon, basically the same time. That was a bit further to the south, where they do have a more thermal. They do have a response that looks like there's some thermal support for the high topography. But when you actually really dive into Wieson's model and look at the sort of area where the CTAM line is, which is just at the margins, it does look like there's a bit of a thicker potential well, how do we say it? That's not actually at odds, right? The seismic model does show potential for a thicker, high velocity region at this part of the TAM. And one of the things to be aware of with the seismic tomography models is they're really sparsely sampled. So this Miller right here is the only seismometer in this region of the Transantarctic Mountains. So they're very coarse, the seismic models. And the other thing Phil was a real champion of was you know, using the 3D codes even in 2D profiles. So there's just a little sort of illustration of the benefit of using a 3D code for this, because we also computed an inversion using 2D code. And while it's broadly similar with the, you know, the sort of near surface or shallower conductive features and, you know, this sort of resistive zone, a lot of the detail and structure you get from the 3D is just missing. So just because we have a 2D transect doesn't mean we shouldn't use the 3D tools. Was one of Bill's big argument, you know, mantras, and I think he's not wrong. But this is a really good example of the benefit that you can get from the additional inclusion of the 3D approach, especially since we all know the world is 3D. All right, and I'll quickly just show some of the Erebus stuff. So Erebus is the southernmost active volcano. It's huge. It's 4,000 meters high. It maintains an active lava lake, and it's a phonolite, which is an odd magma type. This is just a view from the helicopter at the summit. Right, it's actively degassing. It's got the lava lake. It's a phonolite, which is a strange magma type. It's very high in alkalines, low in silica, indicating not a huge interaction with crustal materials and a deep source potentially. So this is sort of one of the ideas, is that it comes from a sort of a plume type setting, basanite evolving in sort of stacked chambers, but not interacting and incorporating much crustal material. So this sort of stacked set of magma chambers is the sort of petrologic idea for this. It's been difficult to get a geophysical picture. Seismic struggled, as I mentioned, with the ability to get energy into the system, right? So they've got this sort of really in the uppermost crust, a seismic tomography model showing something, is present underneath the center, underneath the vent and the lava lake, which of course, but no real connection to depth. And then the large scale tomography, kind of comes to about 50 kilometers and then stops. So there's this big gap, and that's a wheelhouse for MT, right? That's where we're pretty good at this stuff. So we went and we did a huge survey over 3 seasons, 130 odd sites, tremendous amount of work. And what you see here is, there's a lot going on tectonically with the area, right? Mount Erebus is at the southern end of the Terra Rift segment, which runs about 400 kilometers, and at the northern end is Mount Malvern. So you've got 2 volcanoes at either end of this big rift system. You have this red line denotes sort of where the more recent monolithic deposits are on the southwestern side of that red line. And you see there's coincidentally, I don't think it's anything meaningful, but there's a definite change in the characteristic of the phase tensor responses on that part of the island. So I will quickly, one last video, maybe this from up at the top, just so you get an idea of the spectacular views and what the area is like. And I thought this was a good opportunity to show some of these things, and what motivated Phil and others like myself to go and work in these areas that we typically don't get to share. So yeah, just a pretty spectacular but harsh environment. But this is the model results, and in the very near surface we get that sort of large scale conductive halo around the volcano, which we attribute to alteration of young volcanics into clays and such. And as you move a little deeper, there's a very focused pipe under the summit of the volcano. A bit deeper, it broadens and is shifting westward, and deeper again, broader and shifting westward, and then actually does a bit of a banana to the north and hooks to the south at greatest depths. And this is what it looks like. So what we thought is that this is actually, rather than a series of staged magma chambers, but perhaps they're not vertically oriented, right? We have this bounding features where we have this sort of sharp step over that happens sort of at the base of the crust around the moho level. And that we thought, which is here, the moho. And the other interesting thing is that this makes it all the way to the surface, which we don't see in other more H2O dominated systems, like the work at Mount St. Helens, right, where we did the measurements while it was erupting. We still had a top of our conductive anomaly at 4 or 5 kilometers depth. So whereas Erebus comes right to near the surface. So this this is sort of the two big differences that we see is we've been able to follow this system down into the sort of that 100-kilometer source zone depths, and with this shift and getting to the surface. So what this we interpreted to mean is that this sort of western boundary lined up really well with that large scale graben bounding faults of this discovery graben that have been identified previously. So that's sort of a crustal weak zone, which a sort of structural control, if you will, for this guiding this upwelling. And then when it gets to the base of the crust, that's where we have this transpressional dilational end of the rift segment, and inferred fault from aeromagnetic data running across the island, basically along from west to east, that crosses right around where these volcanoes are. So the idea is that we have this upwelling magmatic system interacting with these structural controls and a sort of fault valve system at the base of the crust, where we're getting this evolution and this lateral migration of the magma into a zone where it could actually ascend to the surface. We did some testing to make sure that this was, believable, that we're getting these structures at depth. To do this, we clamped the model at the base of the crust and wouldn't let it. We wouldn't let it put any structure beneath that depth. We computed a forward response from that, and then use that forward response to generate and to reinvert. And what we're seeing is that when you don't have any signal from the base of the crust, we're not reproducing the observed model, right? So there is something in the data that's controlling and requiring these deeper structures, is basically what this is showing. And in 3 dimensions, this is what it looks like. Where we have coming to the surface, the 2 pods, the yellow being a 15-ohmmeter shell, I think, no, a 30-ohmmeter shell, where we'd expect, elevated, thermally elevated, but perhaps not a lot of molten material. And the red is a 12-ohmmeter shell, which is where you expect to have some melt present. And here's that supposed Erebus fault I mentioned, where we think that we're getting this fault valve behavior rather that's controlling this as controlling the evolution, right? Providing the sort of staged resonances of the magmatic system, whereas every so often enough magma pools and builds beneath this fault and generates enough pressure to sort of open the valve and move into the upper part of the system. And that one of the reasons we're able to follow this system all the way to the surface is because it's a CO2 dominated system. It's not got that same sort of viscous stalling that we get with the H2O dominated systems. So I think that's probably a good place to stop. And yeah, this has hopefully been interesting for everyone and a bit of a summary of Bill's career. So, thank you.
Yeah, thanks very much, Graham. A lot of claps are coming in. Yeah, my first interaction with Phil really was during 1986 in the EMS lab experiment in Oregon.
Yep.
And Phil, I was just amazed how he was able to take all the different data sets from different systems and combine them. And then, as you said, in those days, it was forward trial and error modeling in 2D. And Phil produced those models that are published in JGR. And they've stood the test of time, you know, modern acquisition and modern inversion, and not improving much on Phil's models from that time. And I was always impressed. I mean, Phil was very special. Most people who come to MT come from physics, but here's a guy who came from geology and petrology, and he comes in and he masters numerical methods and electronics and instrumentation. He was a true all-round scientist, absolutely.
Yeah.
It's really unfortunate we've lost him. It really is. So I'll get to the questions now, and I've seen we've got 2 questions. There's a number of people in the chat who are saying thanks very much, from Richard Smith and Marie Green, and a load of people who are saying thanks very much in the chat. And yeah, thanks from everybody, Graham, for this. And now to the questions. And the very first one, I think, is quite apropos. It's from George Jurassic. And hi, George, great to see you. Of course, there's Mount Jurassic, which is 450 kilometers north of Mount Erebus. So
Yes. Yeah.
Mount Jurassic, of course, is named after George. So I think it's quite apropos that George is asking the first question. And his question is, did the Antarctic MT results add any insights on the stability of the ice sheets?
I think that there is great potential for that. And Carrie Key's recent work with in the Willans ice stream area is sort of got a bit more of that sort of a focus, but definitely having an idea of where there's, you know, a higher thermal flux just generally would be relevant to those questions, right? You know, if we have a higher thermal regime, the ice sheet is got a, you know, another worry, so to speak.
Yeah. I should just mention to everybody, if anyone wants to jump in and chat, just raise your hand and I'll make it live. And perhaps you want to ask Graham a question or just add a particularly
Story about Phil or something. Yeah.
A story about Phil. Yeah, that'd be lovely. The next question is from Dennis Woods. Hi, Dennis. Great to have you here. Graham, thank you for highlighting Phil's amazing career in geophysics and geology. I hadn't fully appreciated the fact that his entire 40-year career was largely funded through soft money research grants. And I also understand now that one of the primary reasons for success with this funding model is that he always thought big.
Yep.
From large aperture surveys to see the big geological picture, to understand the entire magnetometer process from source to measurement. Big ideas with big results require big and continuous funding. And so now the question, were there empty sites inside the caldera of the Mount Erebus volcano?
Yeah, yes, depending what you mean by caldera. Let me see if I can get a good photo. So you can kind of see in this photo, right, there's this bench at the top of Erebus. And that's the summit plateau that we call it. And that's the boundaries of the last big eruption of Erebus. So that would be the caldera, if you will. On that summit plateau, which is about a 5-kilometer diameter, we made 5 measurements up there. There isn't one sort of there's not one in the crater,
Yeah.
but there is a measurement that's a walking distance to the crater. So we put aside and then we walked up to the rim one day
Uh-huh.
in about 40 minutes.
Yeah.
So on that summit plateau, there is, five measurements. Yeah.
Catherine Schwalenberg had your hand up. I've just allowed you to talk.
Thanks, Graham. But sorry, this was a lost hand. Sorry about
Oh,
that.
see. Oh,
No questions. Great talk. Thank you.
But George, you had your hand up. George, I've allowed you to talk now if you wish to. No?
Mute. Can you hear me now?
Oh, there you go. Yeah. Hi, George.
Hello, guys. Hey, Dobry Grano, Graham.
Thank you, George.
Yeah, I think you speak Czech now, I would guess.
A little bit, not well.
Not well. Well, look at guys, I was there in 1964, 65, and there were mountains left over, hadn't been named, so they went and named mountains for people like myself. I don't know if there are any mountains left in Antarctica, but I'd like to lead an effort to get one named for Phil Wannamaker, if it's possible.
That's already underway, George.
It is. Well, let me put my 2 cents worth in there then.
But
If I can.
actually, the advice was not to discuss it and make anything of it until it's much further along.
Okay. I'll go along with that.
So we can talk about it privately at another time if you want.
Sure, let's do that. The other thing I would add, having spent time, well, I guess first in 1979 with Phil when he was a student of Jerry Holman's at the University of Utah. And then over the years, doing a whole lot of things with Phil, including New Zealand. He was a lot of fun. He was just a fun guy to be around, and just, it's one thing doing all this neat science. It's another thing just being around people you really, really like and enjoy. And I wanted to emphasize that part. So I have to go catch an airplane, guys. So I'm gonna, I'll sign off. But thanks so much, Graham.
Thanks, George.
Yep.
Yeah, thank you, George. Is there anyone else who's got any questions or? Yeah, perhaps I'll just wrap up then by saying thanks very much, Graham. You've really brought home what a consummate Renaissance scientist Phil was. I tried to hire him into the GSC actually in 1988, I think it was. We had a position, and I got Phil to come up, and I courted him, but he was in love with Utah. Didn't want to leave.
Yeah. Well, we tried to get him to come to New Zealand at one point. The same thing.
Okay, we've got a couple of people. Marie?
Yes, I just wanted to express my gratitude. George said it straight out. Yeah, he had the left-right brain going really well and his heart interacting, and it was really fun to spend time with him in the field and work with him in Salt Lake. And I really loved him, and I'm grateful that he's a huge part of my life and my MT career.
Yeah, thank you, Marie. Dennis?
Yeah, Alan, just a comment on your comment about him never wanting to leave Salt Lake City. When he first got the position as a PhD student under Stan Ward, he was just thrilled. I mean, he was bouncing off the walls when he got news of this. And then I, talked to him. Another thing, he's tremendously hospitable. Every time I went to Salt Lake City, he would just always have a party, or he'd be welcoming people. And I asked him, why are you just hanging around here all the time? Why don't you go somewhere else in your career? And he just said, there's no way. I just love this place too much. the mountains, the research, everything. And it doesn't surprise me that people tried to get him away from the place, and it doesn't surprise me that he never jumped.
Yeah. Did you teach him, Dennis, when you
You know,
were?
I'm trying to remember what I think we crossed when I was maybe finishing my master's and he was an undergraduate.
Okay.
Or I must have seen him afterward. When I first came back to Queens, he must have been just finishing. Did he do a master's at Queens as well as a
No, just
Oh.
just an undergrad.
just an undergrad? So he would have graduated in what, about 78, something like that.
Yeah, that's before your time, right? Yeah.
Yeah, that's right.
Mm.
So no, I didn't interact then.
Well, thanks very much, Dennis. Yeah, it's a good day, I think, for everybody to think about Phil's contributions, and also, you know, we have lost very recently another close friend and colleague of Phil's, Louise Pellerin. So, yeah, it's a sad time. All right, thanks again, Graham, and we'll see everybody next week. I'll put this recording up online as soon as I get it from Zoom. And then if you want to send me your PowerPoint, Graham, I'll put that up as well.
I can do that. Yep.
Thanks very much, Graham, and thanks everybody. I see the lineup of people who attended our roll call of some of the top people in our field, and thanks everyone for listening in. Goodbye, everyone. Bye, Graham.
Bye.